Hello all. As I promised, I will be uploading a video on differentiation basics once. So here I am with this video. Please don't mind with the alignment and some noise problem, this and that. It's not recorded in a professional manner. Let me start. Differentiation. It is also known as derivatives. What we actually do in this particular topic, that we need to find the, let me just give you the definition, that what is differentiation all about. We find the slope of tangent to the curve, let us say at a particular point. So what is the meaning of this word slope, tangent and then curve? Let me consider the Cartesian plane like this. Let this be a random curve. This be our x-axis and this be the y-axis. What is the meaning of a tangent? Tangent is a line which touches the given curve at one single point. So the definition has to be noted down. It is a line. It's a line which touches the given curve at one point. So if we talk about a tangent here, let this be that point from where the tangent is going to pass. So this is the required tangent, thus it is passing from this point. So what is the meaning of slope? Slope definition is, which ICSE people have come across in class 10 also, that slope is equal to tan theta. The tangent of the theta is called the slope. What is the meaning of theta? Theta here means inclination. Now what is the meaning of inclination? I'll just write on the definition of inclination first, the technical definition of inclination. That inclination is the angle made by the tangent with the positive x-axis in the anti-clockwise direction. So inclination, this is the angle theta. So inclination is the angle made by the tangent with the positive direction of x-axis in the anti-clockwise direction. That is why I have shown this arrow. So what is the definition of inclination? It is the angle made. So this is the definition of inclination. It is the angle made by the tangent with the positive direction of x-axis in the anti-clockwise direction. This particular word, these two words are very important. The angle made by the tangent with which axis? It is the positive direction of x-axis. We're talking about this axis. And in the anti-clockwise direction, that is why I have shown this arrow. So this is theta. Suppose if my theta is 45 degree, I'll put that theta here. So tan 45 will give me the value 1. So I'll say slope is equal to 1. So this was the definition of inclination. Now let me explain you this concept of slope with one more example. Yeah. So we can see it's again a Cartesian plane, rectangular coordinate system. Let me plot distance on the y-axis, time on the x-axis. So this type of figure, this type of curve we have seen in junior classes, maybe class 8 or 9 in physics, distance time graph. So there we used to read one line in the book, that slope of a distance time graph gives speed. What is the meaning of this? So this, the way we write the name of the graph, that carries one important information. I'm writing distance time graph. The first word is distance. So this parameter will come to the y-axis. I have discussed that in the class also. The second parameter, time, that will come to the x-axis. Very simple. While writing the name of the graph, whatever is written in the first will come to the y-axis. So distance y-axis, I have taken distance on the y-axis, and time belongs to the x-axis. We have taken time on the x-axis. The formula for slope, we have one more formula, that is parameter in y-axis upon parameter in the x-axis. So for this particular case, what is the parameter in the y-axis? It is distance. So let me write distance. What is parameter in the x-axis? It is time. Distance by time, we know the formula, it is speed. So I can say slope is equal to speed. That is what we have written here. Slope of a distance time graph gives us speed. So this we have read in the junior class, but we never tried to find the meaning of the slope. The slope which we are talking is actually about this only. Slope is the parameter in the y-axis upon the parameter in the x-axis. If we bring this definition and modify it little bit, I'm talking about this definition only. Let me modify it in a little different manner. You can write slope is equal to change in y upon change in x. This you can recall ICSE class 10. In the class 10 syllabus of ICSE, we have already done that slope is equal to y2 minus y1 upon x2 minus x1. That is what I have written here, change in y upon change in x. This y2 minus y1 by x2 minus x1 can also be written in this way, delta y upon delta x. What is the meaning of delta? Delta means change. We'll remember that. This is the language of calculus, that whenever we want to denote some change in any parameter, we denote it with the Greek letter delta. So y2 minus y1 I have written as delta y, and x2 minus x1 I have written it as delta x. So bringing that final equation, slope is equal to delta y upon delta x, where delta denotes change. In calculus, if delta is, I'm writing, if delta is very small, then delta is replaced with d. That is one thing we have to understand. If your change is very small, what is the meaning of very small change? Suppose my y1 value is 1.999 and my y2 value is 2.000. So what is my delta y here? That is y2 minus y1 is equal to 2.000 minus 1.999. It is equal to something 0.001. We can easily say that this change is very, very small, and that is why this delta y now can be substituted as dy. As I said, if delta is very small, substitute delta with d. So here we are making one small assumption that delta is tending to 0. What is the meaning of delta tending to 0? Delta tending to 0 means the change is very small, and that is why slope now can be written as, instead of delta y by delta x, I can write dy upon dx. And this is what is called as derivative of y with respect to x. We pronounce it as ddx of y. Taking it here, we pronounce it as ddx of y. Now in calculus we will be dealing mostly with functions, how to deal what type of function, and generally in calculus the most two important category of function we will be talking about is like in function we have two types of variable. We are actually talking about variable here. We have two types of variable. One is the dependent variable, and the next is your independent variable. What is the meaning of this two and how it helps us in selecting a particular parameter in differentiation, that we will understand now. So let y be any function which is a function of x. So I am writing y is equal to fx. Since y is depending on the value of x, so y is known as the dependent variable, and x is known as the independent variable. Whenever we are finding dy by dx, it implies we always calculate the derivative of the dependent variable with respect to independent variable. So I'm writing dependent variable as dv and independent variable as iv. So this point is very important, that always we calculate the differentiation or derivative of the dependent variable with respect to the independent variable. So if for any case I am writing like this, dx by dy, so we can easily say what is the dependent variable. Dependent variable is now x, and what is the independent variable? It is now y. So in this case the function was x is a function of y. So we always find the derivative of dependent variable with respect to the independent variable. Now, having discussed this, we are now in a position to discuss the various formulae of differentiation, followed by some fundamental theorems. That is, how do we apply those formulae to various categories of questions. Let me come to that now. So here is a list of basic differentiation formulas. Like I'm having some 15 of them in front of me. So I'll explain each one to you in some detail, and we'll see that there are certain formulas which have been repeated in here, and why we have written those things in the formula sheet, because it will make our certain calculation easier. So in R.D. Sharma or in M.L. Agarwal or any other calculus book, you will find that you have some basic 11 formulae for class 11 level and 6 additional formulae, that is inverse trigonometric differentiation. That formulae is there in class 12. But for class 11, some 11 formulae are there. I have converted those 11. I have just expanded a little bit and have given you 15 formulae. Let me first discuss the second formula. The second formula talks about ddx of x power n, n stands for Nepal. So ddx of x power n is equal to nx power n minus 1. How can we just simplify this formula? Like, how can we memorize this formula? That if we have any function where we have x in the base and there is some power, some constant value in the power, like n, so whatever power is there, that comes and sits in the front, and the x now reduces by 1. The power of x reduces by 1. For example, if I tell you, they ask us find the ddx of x power 7. So if we try to correlate, what is the value of n now? X power n, x power 7. So I can say n value is 7. So as per this formula, the 7 will come in front. So I'll write 7 came in front, then x, and then the power will become 7 minus 1. So it is 7x power 6. I hope it is clear. The formula is ddx of x power n is nx power n minus 1. Whatever the power was there, that will come and sit in front, and now the power reduces by 1. So it was x power 7, 7 came and sat in front, and now the power is x power 6. Another example, if we take ddx of x power 25. So I guess you must have guessed the answer. It will be 25 x to the power 24. As simple as that. Now coming to formula 1. The formula 1 is ddx of x is 1. We did not memorize this. The second formula is the standard one. If you understand the second formula, you can eliminate 4 more formulas from this list. So I'll explain you the first formula in terms of the second one. So I hope as of now the second formula is clear. ddx of x power n is nx power n minus 1. Whatever original power was there, that came as the coefficient, and now the power of x reduces by 1. So the first formula now, ddx of x is equal to 1. How can I write this? Can I write ddx of, instead of writing, I can write x power 1, right? So this ddx of x or x power 1 is same thing. So as per the second formula, the power is 1. 1 will come here. Now x power will reduce by 1. So 1 minus 1. it will become 1 x power 0. X power 0 is 1, 1 into 1 is 1, one answer is 1. And that is why we memorize this formula, d dx of x is equal to 1. Coming to 7th one now, d dx of 1 by x. Again with the same formula I'll do. Can I write 1 by x as d dx of x inverse? Simple. 1 by x can be written as x inverse. Okay. So as per the second formula, minus 1 will come here. X will remain. Whatever power was there, it will reduce by 1. So it is minus 1 x minus 1 minus 1. It will become minus 1 x power minus 2. Or I can write minus 1 by x square. This was the answer for the 7th one, minus 1 by x square. Come to formula number 8. Same method we can derive it. Formula number 8. Instead of writing root x, I can write x power 1 by 2. So that I'm giving you as a task. Formula number 8 to be derived by you. So basically formula number 1, 2, 7 and 8. They don't have 4 varieties, that is coming under one single variety, that is formula number 2 only. The basic governing formula for all these 4 formulae is formula number 2. Now this one is most usable formula, number 3rd, that is d dx of any constant is equal to 0, that we have to memorize. Coming to formula number 9 now. So one by one I'll explain it, maybe not in a sequence. Whatever comes in an easier way, I'm discussing that. So far we have covered 1, 2, 3, 7 and 8. Now coming to 9, 10, 11, 12, 13 and 14. These are some trigonometric formulae. Here we don't have any concept to understand. We have to memorize it. So d dx of sin x is cos x. But d dx of cos x is minus sin x. This has to be paid little more importance. Little more concentration here you require, that d dx of sin x is only cos x. That is a positive cos x. But d dx of cos x is negative sin x. So d dx of cos x is negative sin x. d dx of tan x is sec square x. d dx of sec x is sec x multiplied by tan x. That derivative of cot x is negative cosec square x. So again in this formula we are getting a negative sign, formula number 13. And even in the 14th formula, d dx of cosec x, we are getting a negative cosec x multiplied by cot x. So formula number 9 to 14, we have to memorize it as such. This 9 to 14. So what are we left with? We are left with 4, 5, 6 and 15th. So let me go to formula number 6 first. This is d dx of log x. It is 1 by x. How do we write log? This is log. This is element. The x is the element of the log and this e is the base of log. So log without element and base is incomplete. So whenever we write log, it is mandatory that we have to write the element as well as the base. Differentiation is a part of calculus, and in calculus, whatever formula we discuss in terms of log, the base is always e. E is also known as natural logarithm. So I'm just writing here, base e is also called natural logarithm. So whatever formula we discuss in in calculus, all formula, if it's a log, all formula in terms of base e. So what is d dx of log x? It is 1 by x. This also we have to memorize it. Coming to formula 4 and 5, I would like to say one thing, that formula 4 and 5 are not two different formula, they are the same only. How we'll see that. Let me discuss formula number 5 first. It is a constant. A is a constant to the power variable. So what is the formula type here? What type of function we are dealing with here? That the base of the function is a constant, a is a constant, and the power is a variable. If such is the case for the differentiation, what happens? The same thing appears multiplied by log that base. Base means I'm talking about the log constant. And of course, as I said, it's a calculus thing which we are dealing with. So always the log will come with a base e. So the answer for this particular formula, d dx of a power x, so whatever we have taken, that will come multiplied by a log whose base will be definitely e, and what will be the element of log? Whatever constant was there in the original formula, that is a. So it will come log a. If I would like to write the same in terms of some other constant, for example, if I want to write like d dx of b power x. So b is a constant, x is a variable. I can write the same thing has come, b power x into log b basis a. I hope there is no doubt. Similarly, if I would like to write ddx of c power x, so it will become c power x log c base e, right? So anything, whatever of the whatever function we take of this type whose base is a constant, whose power is a variable, that will come as such multiplied by a log term, and the element of the log will be the original constant, and of course there will be a base e. So we have seen b power x log b, c power x log c. Same type of function we have here, e power x, whose answer I have written e power x. Actually it should be as per this and this. The answer should have been e power x log e base e, if I am not wrong, correct? But in log, the value of this term, when the base and element of log are same, the log value vanishes and it becomes only 1, and that is why e power x multiplied by 1 is equal to e power x. And that is why this is the formula, that whenever we are doing the ddx of e power x, it is only e power x. We don't have to write this term, because this term writing and not writing is immaterial, because this will give us only 1. E power x log e base e, and this is when the base and element of log are same, the log value becomes 1, and that is why e power x multiplied by 1 will give us e power x. So we have discussed formula number 4, 5 also. Now we are left with just one formula, that is 15th. It is not a formula, it's a kind of an algorithm, that whenever you encounter such a case where you have to find the differentiation where two things are multiplied, k is a constant here, so this k is a constant and fx is a function of x. So whenever we encounter any such thing where we have to find the ddx of some constant multiplied by a function, in that case the constant comes out of the differentiation. So this constant has come out of the differentiation and ddx of fx remains. So that is what we have written, ddx of fx remains. If we take an example for this particular case, for example, ddx of 4 sin x. So what happens? The 4 comes out, ddx of sin x remains. Now whatever is the answer for ddx of sin x, 4 into what is ddx of sin x? As per this formula, ddx of sin x is cos x. So we'll write 4 into cos x. So answer is 4 cos x. Let me take one more. ddx of, let us say, 4 x power 4. This is the question given to us. So first of all, what will happen according to formula number 15? The 4 will come out. So what is remaining? ddx of x power 4. That is equal to 4 is remaining outside. What is ddx of x power 4? As per this formula number 2, that is 4x 4 minus 1. So we'll write 4x 4 minus 1. That is 4 into 4, 16 x cubed. This is the answer. Yeah, now we are going to discuss the fundamental theorem. That is the last part of the basic concept of differentiation. So after dealing with these 3 fundamental theorems, we will be in a position to solve various questions. So in this video, I'll be completing the topic with discussing all these fundamental theorems. Maybe we'll take one example each of these theorems. So the first theorem says that if we get a differentiation where we have various functions separated with either a plus sign or a minus sign, so we can see fx plus minus gx plus minus hx plus minus, it can be anything, it can be 3 term, 4 term, 5 term, whatever it can be. So it's a simple theorem that whatever ddx you are getting, whatever function is there in with us, various terms are separated with either a plus sign or a minus sign, the ddx will be distributed to each one of them with whatever sign they had, that sign will come in between them. For example, ddx of fx plus minus gx plus minus hx plus minus something 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 is equal to ddx of fx separately, whatever sign. If it was a plus, we'll write a plus here. If it's a minus here, we'll write a minus here. So ddx of fx plus or minus ddx of gx. So second function was gx, third function is hx, so ddx of hx, and so on. This will continue. If you're having 5 functions here, we'll write this thing for 5 times. For example, if we take one simple example here, so let me see that example. Suppose d dx of x square plus sin x plus e power x. That has to be written as d dx of x square plus d dx of sin x plus d dx of e power x. d dx of x square, we know it will 2 will come x, now power will become 1 less, so it will become 1. d dx of sin x, direct formula, will write cos x, and d dx of e power x is e power x. So this is our final answer for the first case. Suppose we would have had a minus sign here between sin x and e power x. If you would have had a minus sign, so here also would have given a minus sign. That is the only difference. So that is fundamental theorem number 1. Nothing else we discuss here in the fundamental theorem number 1. It is very simple, that whatever is the function given to us separated by a plus or minus sign, we will just give the d dx to each one of them, maintaining the sign intact. Coming to the second fundamental theorem, it talks about, suppose we have two functions fx and gx in the multiplication form. This is also known as product rule. So I'll write it down. It is also known as product rule. So we can see two functions are getting multiplied. So we have a simple logic here that you keep for first function, let this fx be the first function and gx be the second function. So you keep first function out of the differentiation, differentiate the second function. We can see d dx of g power x, not g power x, sorry, it is gx. So we have kept fx outside the differentiation, we have differentiated gx, we have given a plus sign. Now vice versa, we will keep gx out of the differentiation and will differentiate fx, as simple as that. So I can write, suppose if this is my first function and this is my second function, so I'll write first function into d dx of second function plus second function into d dx of first function. If the same rule we want to extend for three functions, so I'm just writing it. Let us say we can write as 2 extended version. Suppose we want to find out the d dx of fx multiplied by gx multiplied by hx. Three functions have been given to us. Simple. I will not write in terms of fx, gx and hx. Let this be function number 1, this be function number 2 and this be function number 3. So the differentiation is very simple. What we will do, we'll keep first function multiplied by second function outside. We'll differentiate the third function first. Give a plus sign. Now I'll keep 1 and 3 in the multiplication form outside and we'll differentiate the second function. Plus, let us keep second and third function outside and now it will be d dx of the first function. So every single time we have to differentiate any one of these three functions, and whatever we are differentiating apart from those two, apart from that function, the remaining those two will be kept outside the differentiation. The simple logic. 1 2 d dx of 3, 1 3 d dx of 2, 2 3 d dx of 1, and every single time we have a addition here. That's the extended version of second theorem. Here we have taken for fx multiplied by gx, here it is fx multiplied by gx multiplied by hx. That is the thing. So if we would like to take one example here, so let me take it. Example, find out d dx of, let us say, sin x multiplied by e power x. So we can easily judge that we have two functions, sin x and e power x. Let me apply this fundamental theorem number 2. Let me keep sin x outside, give the differentiation to e power x first, give a positive sign. Now let e power x remain outside and now we are giving the differentiation to the first function, that is sin x. As simple as that. Correct? So it will become sin x, d dx of e power x is e power x plus e power x, d dx of sin x is cos x. We should note one thing here, that sin x was sitting idle. It was outside the differentiation, so it will not be modified in any way. Sin x will come as such sin x. Now what is d dx of e power x? We have the direct formula, it is e power x, so we have written here. The plus sign has been carried forward. Since e power x here in this term, in the second term, e power x was sitting idle outside the differentiation, we have carried forward the e power x as such. d dx of sin x, we have the direct formula, it is cos x, so we have written cos x. Now this has become the final answer. If you want to take a e power x common, we can take that. The final answer will become sin x plus cos x. That's it. Coming to last but not the least, the third fundamental theorem. It is, we can see the function is in the numerator by denominator form, fx upon gx. This is also known as quotient rule. So third is also known as quotient rule. What is the function? It is fx upon gx. So we can say we have a numerator, we have a denominator. The function is very simple. We can see that in the denominator, whatever denominator was there in the original function, that has been squared. So okay, we have to square the denominator. That we have understood one thing. And firstly, what we are writing, we're writing the denominator multiplied by ddx of numerator. Wow. Okay, let me write it down in the denominator form. Denominator multiplied by ddx of numerator. Okay, we have a minus sign here. Then fx, that is numerator. Now numerator multiplied by ddx of denominator upon denominator square. This is the standard formula. So that we have to memorize, that gx denominator multiplied by ddx of numerator. Fx is the numerator. Then we have a minus sign. Now fx, that is the numerator. So numerator multiplied by ddx of denominator. And in the denominator, we have finally the denominator square. G of x was the denominator, it has become square. So the formula stands denominator into ddx of numerator minus numerator ddx of denominator divided by denominator square. This one important, very important. The third one is really very important. We'll find maximum usage of formula number 2, theorem number 2 and theorem number 3 while doing the sums. Let me take one simple example following the quotient rule. So this is the question in front of us. Find ddx of sin x upon log x base e. So we can correlate this question with the third theorem, that we have a numerator by denominator form. Let me apply the theorem first. That in the numerator we'll write the denominator first. Okay, log x e multiplied by ddx of the numerator, that is sin x, minus numerator multiplied by ddx of the denominator, and this whole thing is divided by denominator square that we have given. Now log x is remaining outside the differentiation, it will carry it forward as such. ddx of sin x, we already know it is cos x, minus sin x is outside. ddx of log x, we know it is 1 by x. These are direct formulas. You have to refer the formula sheet for that. And this is log x whole square. We can easily see that this can't be evaluated further, so this becomes our answer. So this is the final answer. The maximum which we can do is, we can take x LCM and we can make it x cos x into log x minus sin x whole divided by x into log x whole square. That simplification we can do. We can leave the answer here also, and we can leave the answer here also. These both are correct. But what I wanted to show you is the basic application of this quotient formula. This is how we break the function. This is how we proceed with the differentiation of such a function. So that will be all for this basic video. I seriously think that you must have understood whatever I wanted to convey you. Still facing some difficulty, you can always ping me and drop us feedback. You may drop your comment or mail us the Ashish Academy at gmail.com. Thank you.